Or light could be a particle. So we got a wave or a particle. When we treat light as a particle, we call it a photon, right? Photons are massless, which is weird because they have momentum. They travel at the speed of light, which is, again, it makes sense because we're talking about light speed here. But when light shows up as a particle, we call it a packet, right? Or a quanta, or it is quantized, as we refer to it, with a specific amount of energy. The idea of light being quantized in any object that is a quanta being plural for quantum, is it has a discrete amount of something. So in this case, light has a quanta or a discrete amount of energy. Think of it like stair steps. You can be on one step or on the next step or on the next step or on the next step. You can't treat it like a slide where you can be at any single possible location. Light, when it behaves as a particle, can only have specific amounts. Think stair step as opposed to a slide. The photoelectric effect helps us prove what's happening here. Albert Einstein performed this in 1905, and this, as opposed to his theory of relativity, is where Albert Einstein won his Nobel Prize. Just a little fun fact for you there. So what he did is he was able to shine light, and when he shined light on a surface, he was able to get electrons to be emitted from it. However, the light needed to have enough energy, which meant if he increased the intensity of light, it didn't move anything. So if he went, oh, well, this light's pretty dim. What if I just turn it up more and I have the same light be brighter? Just because it's brighter doesn't mean it has more energy. And that was the big thing that he was able to discern here, is that what if I use a different energy light? So if I use violet, which is higher energy than red, he was able to produce the photoelectric effect using a violet light because it had a high enough energy. The red light didn't have enough energy, and it didn't matter how much red light he used, it didn't produce the effect the way that the violet did and the blues did. The higher energy was able to get these electrons to move. And the reason why this proves that it was acting like a particle was because the photons would hit the surface, and essentially that energy would transfer from one type to another. Think the way that two pool balls hit each other. Another proof that we have is the Compton effect from 1923. Similar idea to what we just saw, where he's using incoming light to hit some material. But now what happens with the Compton effect is he was sending photons of light, they would strike something, and then he would look at how that incident light scattered afterwards. So he'd send in light at some energy, which would mean it had some wavelength and some frequency, so that this light would hit the material, it would scatter off, so it would kind of reflect away. And what he observed was that the scattered light had a longer wavelength, which meant it had a lower frequency, so it had a lower amount of energy. So if you have a longer wavelength with a lower frequency, it was established that it lost energy, but the speed didn't change, right? It's still moving at the speed of light. So as a result, we lose energy, it doesn't slow down, which then tells us that we have a particle here, right? Because that light was able to bounce off of something and demonstrate that its energy was lower. So ultimately, what is light? What is it? We have what's known as wave-particle duality. Light is a wave, light is a particle. Light can sometimes be a wave, light can sometimes be a particle. Sometimes we like to call them wavicles, just kind of combine the two. The problem is, if it's acting like a wave, that's all it can act like. And if it acts like a particle, that's all it can act like. You can't do them both at the same time. It can't be a wave and a particle simultaneously. Depending on how you look at it, and this is what Niels Bohr studied with the principle of complementarity, is how that long word is pronounced. Some experiments are going to give you a result that's going to lend light to being more like a wave. Some will lend it more towards being like a particle. However, it can't be both at the same time. They complement each other. So to fully understand light, you have to know that they both exist in some way, shape, or form.